Welcome back. So we are into chapter 9 and this is ninth video lecture. So in last video lecture we saw how to derive the strong form for 2D elasticity problem. So a strong form, we had two equations uh, which related stress with the forces, the body force, and the first was del sigma xx over del x plus del y tau xy plus bx equal to 0, and second was del sigma yy del y plus del tau xy over del x plus by equal to 0. Okay, and we combine them together and we said we can write it as wst and then sigma plus b vector b is equal to 0 vector, where delta s is nothing but delta over delta x, 0, 0 delta over delta y, and here delta over delta y, delta over delta x. So this is delta s. Sigma is a vector here, and what is that? This is sigma xx, sigma yy, and tau xy, and b vector is bx and by, denoting the body forces in x and y direction, and 0 vector here, 0 vector is nothing but 0 vector is equal to 0 and 0, like this. Okay, so today we are going to first convert this strong form into the weak form. Okay, so as we do always, there is a test function which is, in this case, sigma will finally be a function of u, yeah, and there is a weightage function. So w, let us say this is the weightage function w vector. Again, this is, we say wx and wy is the weightage function, weight functions. Okay, so what we do, as since this is a vector field problem, the u, which is a variable, which is a which the sigma a function of, u is a vector, u is the test function, is the variable which is vector here. So corresponding weight function will also be vector. Hence w vector has two components, one in x direction, one in y direction. So this is a vector equation, which is the equation of equilibrium. We are going to multiply with this vector to that one. Multiply means dot product, so that we have the scalar one scalar equation, and that we are going to integrate over the whole domain. What I mean to say is, we will multiply w vector transpose and then this equation. So del st sigma plus b equal to 0. Okay, so this will be equal to 0. That's what, but we are going to integrate it over the whole domain, so like this, and the whole thing equal to 0. So what we did, this is a weight function, and this weight function itself is a vector, and we are doing the dot product with this weight function to the origin equation of equilibrium, which is also in form of vector. So this dot products will make all these things, will turn this the original equation, which is vector, into a scalar now, and this we are integrating over the whole domain. Okay. So next is we have to expand it. So if you expand, so here what do we have? We have w1, wx and wy. Okay, and then this equation. Okay, then this equation. So this equation we will write it here. So we have del st sigma plus b t is equal to 0. So okay, expand further. So we have wx wy, and this equation we have, actually you can, if you expand further, this will look like the original del over del x sigma xx plus del tau xy del y plus bx, and second one will be del over tau xy dx and del sigma yy over del y plus by, so plus by, and then we have d omega and everything equal to 0. Okay, so we are just expanding. So since we had combined this into this equation, and this equation we are now, this one is expanding. If you expand it, we get these two, a vector which will have these two rows. So that's what we are doing it here. Okay, so or we get, or if you expand, so this multiplied by this, so this will multiply by with the first row, and omega and wy will multiply with the second row. So what we can write here, we expand it further, so we have wx and then del sigma xx del x plus del tau xy over del y plus bx d omega plus wy del tau xy del x plus del sigma yy del y over by d omega is equal to 0. So we have actually distributed this into two parts. the whole thing into two parts, which will look like this one. We will do the further expansion, or omega wx, and then we have sigma xx over del x plus del tau xy del y, okay, plus d omega plus omega x bx d omega plus omega wy del tau xy del x plus del sigma yy del y e omega plus integration wy by d omega equal to 0. So further expansion, we got it like this one. Okay, so let's see the first one. We will just take this one on the next page. Okay, so wx multiplied by del sigma xx over del x plus del tau xy over del y d omega. So now the very first term of the equation we wrote last in the on the previous page. So that equation is integral omega, and then it is wx, then del x, then sigma xx plus del tau xy del y d omega. This we can write it as equal to omega, then wx, and then we can write it as dot sigma xxi plus tau xy j d omega. Okay, where we know this is nothing but divergence, basically del, where we write where is equal to del over del x I plus del over del y j. So this is divergence that we have used earlier also. So the original one, this becomes equal to, so let's call it omega wx divergence of sigma x vector, okay, where sigma x vector is given by this. So let's write it first here. We write where sigma x vector is equal to sigma xxi plus tau xy z. So this expression becomes equal to two terms. We are applying the integration by parts. This kind of expression we also got when we derived for the heat transfer problem. So here we got W, then divergence of the Q vector. Yeah. So we got W, then del dot Q. So here we have the similar expression, and if we apply the equation by parts, we will get this equal to nothing but this we get divergence of wx multiplied by sigma x vector. Okay, so this minus, so we can write it like here, so this minus, and this becomes wx dot sigma x d omega. So this expression we also got during the heat transfer problem. We are applying the same thing here. It's nothing different, the same thing, only the symbols are different. So instead of w we have wx, instead of q we have sigma x. That's it. So we apply the same thing here and we will get this expression. So we expand it. So what we get is sigma so divergence of wx sigma vector d omega minus we get gradient of wx dot sigma x vector d omega, got like. Now this one again we will apply the divergence theorem here. So applying the divergence theorem, again we got this kind of expression when we derived the heat transfer problems weak formulation. So there we had divergence of w times q, but we have here divergence of wx times sigma vector. So this from the omega integration over the whole domain, we will convert that into integration over the boundaries. So this is converted into gamma here, and this is nothing but simply n dot wx sigma and d omega d gamma. Okay, so we are just replacing this del vector by n vector, where n is the unit vector perpendicular to the surface. So this is what we get, minus omega and gradient of wx dot sigma x vector d omega. So this is for this one, okay, original this one. So similarly the other expression which has wy can be converted in this format. Okay, so we can write here similarly omega wy del sigma rather tau xy del x plus del sigma yy over del y d omega will be equal to we write in this format. So will be gamma n dot w, okay, so here this is sigma x, w y sigma y vector d gamma minus omega del wx dot wy dot sigma x, sigma y in this case, and d omega. Okay, where of course here we have to define what the sigma y is. Sigma y here is nothing but tau xy I plus sigma yy j. So the final weak forms becomes first we write the final weak form, okay, becomes what? First the first equation we derived, so this becomes gamma n dot wx sigma x d gamma minus sigma gradient of wx dot wx d omega, okay, then plus second thing we derived based on this one, so this is n gamma n dot wy sigma y d gamma minus sigma minus omega, integration of over the whole domain omega, then gradient of wy dot sigma y d omega plus bx term, so bx times wx dx and similarly wy and by dx equal to 0. So this is what the final weak form is. Next thing will be to apply the boundary condition, this one, and if we just take these two equations, then let us see how can this be simplified further, and the idea is to express these in terms of the traction so that we can apply the traction boundary condition. Let's look at the first term. So where, so this term, the first term, gamma n dot wx sigma x vector d gamma is equal to, wx is a scalar, so we can move this outside, so n dot sigma x vector, so d gamma. Okay, so now we know that n is equal to nxi plus nyj, as we saw that in the last lecture video. So if we put it there, we get the original equation becomes equal to gamma, then wx, and then this dot sigma vector, so nxi plus nyj dot, and sigma x is nothing but sigma xxi plus tau x y j d omega, d gamma rather. Okay, so what we get, this will be equal to gamma and then wx and then nx. So we get sigma xx nx plus tau xy ny, and we get the gamma. So what is this one? So from the last lecture video you can recognize this is nothing but Tx. That's the traction in x direction, so whole thing becomes Tx. So equal to gamma Wx times Tx d gamma. Similarly, the second, this term also becomes simply equal to Wy times Ty. The whole term becomes Wy times Ty integrated over the whole boundary. Let's write that here. So we have integration gamma of what? Of the original equation, this. So n dot n vector dot w y sigma y d gamma will be equal to, finally, integration integrated over the whole boundary and then Wy Ty d gamma. Now let's simplify these two further. So the terms which we have in the weak functions are omega del wx dot sigma x d omega plus del y dot sigma y d sigma. So if we expand this further, this will be omega, and this one is nothing but del wx over del xi plus del wx del yj and dot sigma x is sigma xxi plus tau xyj, like this. Okay, d omega plus this term, so omega del wy del xi plus del wy del yj dot tau xy I plus sigma yj, okay, d omega. We expand further. If you do dot product here, we will get is equal to omega, and what do we get? I and I terms will combine, so d wx over del wx over del x multiplied by sigma xx, so sigma xx plus del wx del y over tau xy d omega, plus we get this term, so del wy del x tau xy plus del tau xy del wy del y and sigma yy d omega. Okay, both the terms we now combine So inside a single integral, so this becomes equal to, let's look at this. So this becomes del wx over del x del sigma xx. Okay, then let's write this one. So this is del wy del y sigma yy plus then these two, so del wx del y tau xy plus del wy del x tau xy d omega. Okay, so let's again write that in compact matrix form. So let's say we want to write here like this. We want to write here like here sigma xx, sigma yy and tau xy. Why we want to write like this? Because the original sigma vector is like that we used. So let's see what will be if there has to be a matrix this side and how this matrix has to look like. Okay, so sigma x multiplied by sigma y, the sigma x, sigma xx is looks like this sigma xx has to be multiplied by del wx over del x. So we write here del wx over del x. Second term is, so let's write in a column and we'll put transpose here so that it's more clear. So the first term is del wx over del x. Second term, which is multiplied by sigma yy, is del wy over del y, that is the second term. And the third term is these two. So basically del wx over del y plus del wy over del x. You can readily recognize that this form is what we got for the strain as well. So for example, epsilon xx was nothing but del ux over del x. Epsilon yy equal to del uy over del y, and so on. So this is of the same form, and we expect that because w and u are equivalent. Okay. So let's write this vector, this matrix in some known form. So del wx over del x del wy over del y and del wx over del y plus del wy over del x. This becomes equal to what we want. We want in terms of wx and wy here. So there be a matrix which will come here. So which matrix? So let's write it like this and we will fill it up later. So here wx, so this is nothing but operator matrix. So here del over del x will be there, so that if you multiply by this we get this, and here it will be 0, so that 0 is multiplied with wy. Similarly, in this case will be 0 del over del y, so that this and this will match, and third will be del over del y, and here del over del x. If you see the last video lecture, this we called it at del s. So this is del s. Okay, this is okay. So this is del s, and this one is nothing but w. So w vector, just like that. Yeah. So this in compact form. So this we are going to use in the final the final week, the grand final week form. So we are going to combine all of them but in compact form. So the first term we worked on was which had gamma, so we combine the gamma term here. So we had gamma, and then we have w x dx d gamma plus wy dy d gamma. So gamma term is here. Second term is this one, but has to be a negative of that. Okay, so so this is equal to this. However, the actual expression is this. So this is what the sigma, this is a sigma vector. Okay, so we have to also write the sigma vector basically. So the whole thing, if we combine them together, okay, let's write it here, the whole thing. So here this will be plus gamma, and then this term was there, after that sigma term. So this terms becomes del s w, and this is transpose because this was the transpose is. So this we wrote already in compact form, and then this sigma. Now in the earlier lecture video we call it sigma vector. So we just write here sigma like this. Okay, and d omega. Okay, so this term plus we have bx and by term. So we have wx bx d omega plus omega wy by d omega. Okay, so or all terms added together will be equal to 0, or our final form will be, we combine these two now. So what we get is in vector form we get w, this is w, so we get w transpose t. Okay, where t is tx ty, this we are writing in vector form. So that we get both of them. So w is nothing but wx I plus wyj. So dot txi plus tyj will be what this is basically. So we are combining this together like this one, plus this term. So transpose to automatically, okay, this term has to be negative in the original equation. Okay, so this is plus by mistake, so we write negative here, so accordingly this will be minus, okay, minus, and transpose of that, so W transpose, okay, and then WS transpose and sigma, just like this, okay, d omega. Again this also we can write the similar way, and this becomes W transpose and B vector d omega is equal to 0. So this is the final, super final weak form in matrix notation. So where we have to write W, so we just write where W transpose is nothing but W1, W2, and similarly the T vector is nothing but equal to Tx and Ty, and B vector B is nothing but Bx and By, written like this. Okay. The other symbols have usual meaning that we have defined earlier. Okay. Let's check it again. So this is gamma, so it has to be integrated over the whole gamma, so d gamma will be here. This is sort of gradient of sigma, which is not correct, so this we put by mistake, so this one we cannot expand like this one, otherwise this will differentiate sigma that we don't want, because we have already converted this into the weak form. So we will put the same symbol here, so instead of this we will use del SW transpose, like this one. Okay, so here is good, so we will rewrite on the next page. So the weak form that we got finally is, so integrated over gamma, so we have W transpose T, okay, d gamma minus omega, we have del S, then W transpose of that, then sigma d omega plus omega W transpose B d omega is equal to 0. B is also a vector here, where we have W equal to Wx Wy, T is also a vector, so T is the x component of the traction and y component of the traction, and B is the body force, the x component and the y component. This del S is a operator matrix which has del over del x 0, 0, del over del y, and del over del y, del over del x. So this expression, we have sigma vector, which is sigma xx, sigma yy, and tau xy. Okay, all other things have been covered already. So this is the final weak form, which is like this one. Now remember that we also have the relationship between a strain and a stress, and again the relationship between a strain and displacement, that also we can put it here. So we know what we know already, and what one was strain, the stress is a function of a strain, so this is equal to this, where D is a matrix, elasticity matrix. So this sigma is equal to D matrix multiplied by a strain E, where a strain is equal to xx, yy, epsilon xx, epsilon yy, and gamma xy. So this we have, and this is also D is again 3 by 3 matrix that we derived last time, and a strain itself is also related. So a strain is del S U, okay, and where del S we know what that is, and U is Ux and Uy. So this we also got in the last lecture video. Okay, so this thing we can put in this equation to get the further complete version of the weak form. So weak form now becomes we write gamma Wt traction d gamma minus, okay, now we have this Ws, so d delta S W transpose, and sigma we write as d epsilon d omega plus omega Wt b d omega is equal to 0, or so here we have this, again we can put epsilon equal to delta SU as well here. So or we write further gamma W T D gamma minus omega delta S W transpose D, and this is itself ds u, okay, d omega plus integration of w transpose p vector d omega is equal to 0. So this is the final compact weak form, which has no sigma here, no strain here, but we are writing everything in terms of u, means the whole equation is in terms of forces and displacements only. and the weightage included. So weightage has the same unit as the displacement. Now of course you have to apply the boundary conditions, and as you remember, we had the boundary divided into two parts. One is gamma u, where the displacements are prescribed, maybe fixed or some finite displacement is prescribed, and there are others gamma t where the traction is prescribed. So let us say from here to here gamma t is that is where the tractions is given, and there will be some boundary where the displacements are prescribed. So gamma is nothing but gamma u union gamma t. Okay, so we know that this is valid for all w except not except but for all w with some property. And what property? We have w such that w at gamma u is equal to 0 vector. At gamma u w is equal to 0, hence this term will vanish at gamma u. At gamma t this term will be there, because at gamma t some boundary condition will be prescribed, and what the boundary condition will be t equal to t naught at gamma equal to gamma t. So since this is given and at this w vector is not 0, then this term will be there. Okay, so we can put this boundary condition here, and we can also write that with the boundary condition like this. So del gamma, okay, and then we have w t. We write gamma t because when gamma equal to gamma t, then only this term will be there, and this terms becomes t naught, which is prescribed or given, or minus all other terms will be there. So del s w t d del s u d omega plus omega w t b vector d omega equal to 0. Okay, so this is the final weak form with the boundary condition applied. Okay, so in the next lecture video we will actually have the shape functions, and we will express w and u as shape functions, and we will derive the stiffness matrix and force vectors. Okay.